Batteries. Batteries are voltaic cells. They're packaged up conveniently to function as portable sources of electricity. Different types of batteries use different types of chemical reactions. So we are going to talk about different types of batteries. I don't expect you to know the different chemical reactions that occur in the different kinds of batteries. So dry cell batteries, these are very old-fashioned. They don't have a lot of water in them. And so these typically use zinc being oxidized and manganese 4 being reduced. So the overall reaction, we can add these two together. So the word alkaline means basic. So these are batteries that have, the inside is basic instead of acidic. These have a longer working life, they last longer, they also keep better on the shelf in your cupboard while you're waiting to use them. So these have largely replaced the original dry cells. So these are what we now think of as kind of the old school batteries, the alkaline batteries. And here you have an illustration of the inside. Car batteries. Car batteries are typically lead acid storage batteries, and they actually have 6 different cells wired in series so that you can get a total of 12 volts, because you can't get 12 volts from one cell. So each cell here produces 2 volts, which is actually quite a lot for a battery. All of these slides have the 2-half reactions and a place to write the overall reaction. I don't know that it's a good use of our time to do that for each of them. I mean, it's just, we're not going to memorize them. So I just don't feel like doing it this morning. What's interesting here is that both electrodes produce solid lead sulfate. So the oxidation, which is at the anode, is making lead sulfate, and at the cathode, the reduction reaction is also making lead sulfate. And so what can happen with that is if the battery runs for too long, that lead sulfite coats the electrodes. And once it coats the electrodes, then it's very difficult for electrons to get through. And so the battery will run down. These batteries can be recharged with an external current which reverses the reaction. So what's happening in a standard gasoline-powered car, the battery is used to start the car. And you need a fair amount of voltage to get things going. But then once the car starts, it's running on gasoline. Then you have a thing called an alternator, which takes some of the energy from the combustion and turns it into electricity to recharge your battery. So if your alternator is dead, your car will be fine for a while until your battery just runs down, and then it's not going to work anymore. Any questions? There are other rechargeable batteries, nickel-cadmium batteries, NiCad, those are pretty common. So those have cadmium and nickel in them. The overall reaction there is 1.3 volts. We've gotten a lot of rechargeable batteries from IKEA because they're affordable and because I love going to IKEA. But their rechargeable batteries are going to give you about 1.3 volts instead of 1.5 volts for like an alkaline battery. And so what we've noticed is that there are some devices that it's just not quite enough voltage. Some things, it'll run fine until the battery runs down just a little bit. And other ones, it just won't work at all. And so if you're using rechargeable batteries in something and it doesn't seem to be working, try some alkaline batteries because they have a little bit higher voltage. Here, as with the lead storage battery, we get solid products that build up on the electrodes. But if we run the electricity in the opposite direction, we reverse all those reactions, we can regenerate the reactants. If you overcharge the battery, if you run too much electricity in it, that can cause other reactions that aren't wanted and damage the battery. And it used to be a big problem, but now they've come up with smart chargers, right, that monitor potential and they'll stop before they overcharge the battery. Nickel metal hydride batteries. These are replacing the NiCad batteries because cadmium is a toxic metal. And so if you're throwing batteries into the trash and they're going to the landfill, eventually that cadmium can leak out into the water table and it's not good. So nickel metal hydride, we've got the same reaction happening at the cathode, but the anode reaction is different. So here we have hydrogen atoms that are in a metal alloy. So that's what the metal hydride is. And it's the hydrogen atoms that are getting oxidized. You have greater energy density in these batteries than the NiCads, and that means you have a higher energy content per unit of battery mass. Now, if you're trying to power something like a drone that's flying, right, you want those batteries to be as light as possible, right? Because if the battery is too heavy, you're going to expend more energy lifting the battery, right? So you want things to be light. Another kind of rechargeable battery is a lithium-ion battery. So these are newer. They also have high energy density, and these are the sorts of batteries that are in your cell phone and your laptop, your digital camera. These batteries work differently. I'm not going to go into the details of it, but the lithium ions are going to move from the anode to the cathode, which cause electrons to move through the external circuit. So this one works a bit differently, but is still electrochemistry. Then there are fuel cells. So in a way, fuel cells are like batteries, but the reactants can be replenished from an external source. So the most common one is the hydrogen-oxygen fuel cell. We have hydrogen gas flowing past an anode, which is a metal screen with a platinum catalyst. The hydrogen gets oxidized. Oxygen gas is flowing past the cathode. That gets reduced. The only product here is water, which is awesome, right? Because this is not polluting anything. The problem is you have to keep putting hydrogen gas into the cell. Where do you get the hydrogen gas? Well, that's the problem. We can get hydrogen gas from several different sources, but it's not something that you can just get anywhere down Highway 99, right? So hydrogen-oxygen fuel cell-powered cars are possible, but we don't have the infrastructure to make them practical yet. Here's an illustration of that. So we've got hydrogen gas, which is being oxidized, because I'm saying losing electrons. Oxidation is losing electrons, because I have to say that every single time. So, and then we have the oxygen being reduced. And so we need hydrogen gas coming in and oxygen gas coming in. The source of oxygen isn't as important because there is oxygen in the air, right? But there's not hydrogen in the air, so we need a source of hydrogen. there's no recharging this one. If you get pulled over because you're driving erratically, you may be administered a breathalyzer test to see if you're intoxicated, right? One of those breathalyzers uses a fuel cell to measure how much ethanol is in your breath. The amount of ethanol in your breath is proportional to the quantity in your bloodstream. So here's an illustration of that. So we have air intake coming in here, and your breath coming in there. And so the ethanol in your breath is going to cause the potential of this cell to be different. And so they can read your blood alcohol level just from your breath. It's pretty cool. Here's the chemical reactions occurring there. And again, we've decided that we're not that interested in figuring out what the overall reaction is today. But when those are calibrated correctly, you can precisely measure the blood alcohol level of a suspected drunk driver. And this is great because if you're doing a blood sample, right, you can't just do that on the side of the road. And by the time you get someone to a place where that could be, you got to do all this process stuff before you could do that. Their blood alcohol may have changed. And so this is something you can do. It's completely non-invasive. Anyone can be trained to administer it. It's a pretty cool thing. Again, it's electrochemistry.